everyone, in this video, we will be discussing about the measure of kurtosis. And as we proceed to the discussion, allow me to introduce myself. My name is Maria Algilin Saliote, 18 years of age. I was born and raised in Milanilla, Cebu, currently enrolled in City UMC, taking up Bachelor of Science in Mathematics. So for us to be able to pursue the lesson, kindly prepare yourselves any means for taking down notes such as pen and paper. And as an overview, we'll be talking about the definition and understanding kurtosis, the exist types of kurtosis, measure of kurtosis for ungrouped and grouped data, and as well as we'll be answering the kurtosis facts and the bottom line for our conclusion. And after that, I'll provide you one simple question for you to solve, and you'll be giving 10 minutes allotted time. What is kurtosis? In statistics, a measure of kurtosis is a measure of the tailness of the probability distribution of a real-valued random variable. It is used to describe a characteristic of a data set. Kurtosis indicates how much data reside in the tails. The standard measure of kurtosis is based on a scaled version of the fourth moment of the data or population. Therefore, the measure of kurtosis is related to the tails of the distribution and not its peak. Kurtosis is a measure of the combined weight of the distribution's tails relative to the center of the distribution curve, or the mean. Kurtosis is sometimes confused with a measure of the peakedness of a distribution. A distribution can be sharply peaked with low kurtosis, and a distribution can have a lower peak with high kurtosis. Thus, kurtosis measures tailness, not peakedness. However, kurtosis is a measure that describes the shape of a distribution's tails in relation to its overall shape. There are three categories of kurtosis that a set of data can display. All measures of kurtosis are compared against a normal distribution. A negative excess kurtosis represents a platycortic distribution, and a zero value indicates a mesocortic distribution. And lastly, a positive excess kurtosis indicates a leptocortic distribution. If the kurtosis is less than 3, then that is platycortic. And if kurtosis is equal to 3, then that is mesocortic. If kurtosis is greater than 3, that is leptocortic. So this is our formula for measure of kurtosis for ungrouped data. We have K for measure of kurtosis, sample data, its mean, number of data in the sample, and sample standard deviation. So let's have an example. A sample of 5 students obtained the following scores: 80, 88, 92, 90, and 85, with a mean of 87, and the standard deviation is equal to 4.69. Solve for the measure of kurtosis. So let's start with the table first. So we need the difference between the sample data and mean. So our mean is already given, so that will be the 88 minus 87 will be 1, and so on and so forth. Now let's have another column. We will be getting its answer of its fourth power. So fourth power of 1, that will be 1, and so on and so forth. Now we need to get the sum. So that will be 3124. Moving in, let's put the formula for measure of kurtosis for ungrouped data. The numerator, that will be the summation to the fourth power of the difference between the sample data and its mean. So let's change our numerator into 3124, and for the denominator, the number of sample data, that will be 5. And the standard deviation is 4.69. Now to the fourth power, so let's simplify the denominator. First, so you will get around 2419.14 something. In your calculator, calculate first the fourth power of 4.69, and that is when you multiply it to 5. Since we already found our denominator, let's simplify it further, and 3124 divided to 2419.14, and you will get an answer of 1.29. Let's go back to the 3 types of symmetrical curves so that we can know what type of distribution or code this is. So our answer earlier is 1.29 because our 1.29 is less than 3, so our answer is that it is a platycortic, because the platycortic is when the value of kurtosis or measure of kurtosis is less than 3. Moving in, let's proceed to the measure of kurtosis for group data. So this is the formula that we will going to use. We have k is equal to the numerator, the summation of the frequency multiplied to the fourth power of the difference between the midpoint minus its mean. In the denominator number, that will be the number of data in the sample multiplied to the sample standard deviation to the fourth power. In dealing with this formula, you just have to be careful within the order of operations. Okay, so especially its exponent. So have to know if what's the first thing you're going to do. So let's have the first example. In here, we need the standard deviation and the frequency and the other parts of our formula. What I did is that I used another problem for me to be able to have and fill all the data that we need for our formula. So this is the finishing product from our example in order to get our standard deviation and the frequency. We already have the variance standard deviation group data. The problem is if you want to find the kurtosis, you need to have this one, its numerator. This one we have to the fourth power because as we notice in our table, you only have square. It's only square and there's no to the fourth power, so we need to find it. So let's make another column for that one. The difference of the midpoint in the mean. After that, simplify it to the fourth power. So I'll put a color coding on it. The green one is for our value and let's make it to its fourth power. So first, the negative 19 to the fourth power is 130,321. And so on and so forth. For the rest value is standard deviation. And now we have to multiply it to its frequency. That will be in another column. So our frequency is the purple one multiplied to the blue. So 6 times 130,331 21, that would be 781, 926, and so on and so forth. Now we have to get the sum. Add all gold colors in the last column and we'll get a sum of 1,868,346. Let's go back to the formula. Since we already solved for the summation of our frequency and standard deviation, we'll just place it to our numerator. Then for our denominator, our n will be the number of samples, so that will be 108, and the standard deviation is 9.07 to its fourth power. So let's simplify it and we'll get 730,891.49. Remember, you have to do the exponent first. Now let's calculate it and we'll get an answer of 2.56. So therefore, the given distribution is platycortex since the measure of kurtosis is less than 3. Moving in, let's have our kurtosis frequently asked questions. So, why is kurtosis important? Kurtosis explains how often observations in some datasets fall in the tails versus the center of a probability distribution. In finance and investing, excess kurtosis is interpreted as a type of risk known as tail risk, or the chance of a loss occurring due to a rare event as predicted by the probability distribution. Is kurtosis the same as skewness? No. Kurtosis measures how much of the data in a probability distribution are centered around the middle versus the tails. Skewness instead measures the relatively symmetry of a distribution around the mean. Let's have our bottom line. Our conclusion is that kurtosis describe how much of a probability distribution falls in the tails instead of its center. In a normal distribution, the kurtosis is equal to 3 or 0 in some models. Positive or negative excess kurtosis will then change the shape of the distribution accordingly. For investors, kurtosis is important in understanding tail risk, or how frequently infrequent events occur, given one assumption about the distribution of price return. So let's have our question, and you'll be giving 10 minutes allotted time for you to solve this problem. The semi-final exam scores in a statistics class are 63, 64, 66, 62, and 60 with a mean of 63 and the standard deviation of 5, and solve for the measure of kurtosis.
It's your time now. It's your time now.